Welcome. We've been talking about compositions in section 9.5, and we're going to look at one more special kind of composition, and that's a double reflection in this video. And we're going to look at double reflections, meaning a reflection of a figure followed by a reflection of its image. We're going to look at that in a couple different perspectives. We're going to look at what happens when you have reflections in parallel lines, and we're going to look at what happens when you have reflections in intersecting lines. And there's just very cool properties that actually turn out to be true whenever those things happen. Now, you see a picture illustrating a double reflection in a parallel line. This segment VT is the original figure, and you can see it was reflected in this first vertical line. And then that segment V prime T prime was then reflected in the second vertical line. Those are parallel to one another, right? And here's the final image then. And whenever you do a double reflection in two lines that are parallel with one another, there's a special relationship between the original figure and the final image. All right, now, you know that the final image is a reflection of V prime T prime, right? But if you were to try to map segment VT directly onto segment V double prime T double prime, what kind of transformation would make that happen? Well, I hope you can tell that it would be a translation, which is really cool. Anytime you want to translate a figure, one way of accomplishing that is just to reflect it in two different parallel lines. Now, there's another property or two that we need to mention along with the fact that the final image is a translation of the original image, and that property has to do with how far apart is V double prime T double prime from segment VT, its original image. All right, well, we'll show it to you this way. There's a distance between the parallel lines that is worth mentioning right here. Let's just say that the distance between these two parallel lines is D. All right? Well, what always happens is that if you do a double reflection in two parallel lines that are D units apart, the distance of the translation that you would end up with happens to be twice the distance between the parallel lines. So what I mean is that if I were to draw the segment connecting T and T prime, T double prime I mean, right there, that distance would be twice the distance between the parallel lines. And that would be the same for if I were to connect V with V double prime. The distance between those points is going to be twice the distance between the parallel lines. Really cool property, which you can write out this way. The length of the translation is twice the distance between the lines of reflection. Very good. Now I'm going to prove that works to you here momentarily in another example. But I also want to talk about what happens when you do a double reflection in lines that intersect one another. Now we're going to look at sort of a modified segment. It was going to be hard to make the final conclusion I wanted you to make if I just used a line segment into this double reflection. But you see here this modified line segment AB with kind of the flag attached to it. And first, it was reflected in this line that I'll call line M. And then that image is reflected in this second line, which I'll call line N. Now, again, there's a special relationship between the original figure in that double reflection and the final image. If you were to go directly from the original figure to the final image, you wouldn't do that with the reflection. You would do it with a rotation. Can you kind of see that? That's why I put the flag, so you can imagine, hey, if I kept rotating this way, that's the way that it would look. All right? And so it's the same as rotating that figure around the point where the two lines of reflection intersected one another. So we would say that segment A double prime, B double prime is a rotation of segment AB. All right, and it would be a rotation of segment AB about the intersection of the lines of reflection. In other words, if I called that point P, where those two lines intersect, that would be the center of that rotation. Okay, now there's also another property that goes along with that. It's similar to the one we just looked at up here with the double reflection and parallel lines. We said with the double reflection and parallel lines, the final image is a translation of the original figure, and they were twice as far apart as the lines of reflection were. Okay, well, there's another doubling relationship here, but it has to do with an angle. It doesn't have to do with a distance. It turns out if you measure the angle between the lines of reflection, and always measure either the acute angle or if the lines are perpendicular, use the 90-degree angle. If you were to measure the acute angle formed by those two parallel lines, the angle of rotation that would map the original figure onto the final image would be twice the measure of the angle between those two lines of reflection. So let me show you this with point A and point A double prime. If I were to connect those both to the center and then measure the angle between them, it would be twice the measure of what we had to begin with. Okay, the angle between the two parallel or the intersecting lines. So there you go, you can write this down. The angle of the rotation is twice the smaller of the two angles formed by the lines of reflection in that double reflection. Okay, so if you double reflect in parallel lines, you end up with the final image being a translation. And if you double reflect in intersecting lines, then the final image is a rotation of the original figure. Pretty cool. Now let's show you that those things actually work out using some coordinate plane transformations here. All right, first I'm going to look at the properties I just discussed about reflections in parallel lines. And I've got a triangle here. I said in the direction it's triangle ABC, so let me label it. And we're going to reflect that triangle on the line y equals 3 first, which you should know is a horizontal line. And then we're going to reflect it in another horizontal line, y equals -2. Let me go ahead and draw those two lines of reflection. All right, so what's supposed to happen, according to what we just talked about a moment ago, is that when I reflect triangle ABC in y equals 3, and then I reflect it again in y equals -2, the final image ought to be a translation of the original figure, and it ought to be twice as far from the original figure as these two parallel lines are from one another. So, since we can measure the distance between the parallel lines, let's see how far apart they're supposed to be from one another. Y equals 2 and y equals -2 and y equals 3 are 5 units apart, aren't they? So our final image ought to be 10 units away from the original figure. Let's see if that works out. Let's go ahead and reflect A, B, and C in the line y equals 3. All right, you should be able to see that point C is 1 unit above the line, so its image will be 1 unit below. Point A is 3 units above the line, so its image should be 3 units below the line of reflection. And then point B is the same. It was 3 units above the line, so its image will also be 3 units below the line of reflection right here. So there's the first image, triangle A prime, B prime, C prime. All right, now our next goal then is to reflect that in the line y equals -2. So let's go ahead. All right, so you see A prime is 2 units above that line, so here's A double prime. You see that C prime is 4 units above the line y equals -2, so here is C double prime. And B double prime was 2 units above our line of reflection, so there's its image right there. Here's triangle A double prime, B double prime, C double prime. Now part A of our hypothesis is correct. I think you can see how if you were to just translate triangle ABC downwards, it would look like triangle A double prime, B double prime, C double prime, correct? The next part of our hypothesis, or really it's in reference to theorem 9.5 in your textbook, is that the length of that translation should be 10 units. Now let me do this real quick. I'm going to go ahead and write down the coordinates for our final image, because that's really what the directions are asking for. And then the way that I'm going to prove that that was a translation of 10 units in length is we're going to go ahead and take that original figure, ABC, and we're going to translate it using the vector 0, -10. Right? That would move a figure straight down 10 units, which is what our translation would have been. So, if we did that, the point A prime that was at -3, 6 would have its y coordinate decreased by 10, and that would get it to -3, -4. All right, that corresponds with our A double prime. We would decrease the, whoops, hold up, I wrote the wrong points up here. I'm trying to say we're translating A, B, and C, not A prime, B prime, and C prime. Let me erase those primes. Okay, so if I were to take the coordinates for point B, which are 1 and 6, and I were to subtract 10 from the y coordinate, as that vector tells me, I would end up at 1, negative 4. That matches up with our A double prime, B double prime. And if I were to do the same thing with point C, which was at negative 3, 4, that would get us to negative 3, negative 6. So you can see, indeed, that that double reflection gave us the same thing as had we translated 10 units straight down. All right, pretty cool. Now let's look at the double reflection in intersecting lines. All right, this time what we're going to do is we're going to show that when you reflect a figure in two different lines that intersect one another, that first of all the final image will be a rotation of the original figure, and we want to show that its angle of rotation will be twice the angle between the two lines of reflection. All right, now those two lines of reflection are going to be the y-axis followed by the line y equals negative x. All right, so the y-axis clearly is already drawn. Let me go ahead and draw the line y equals negative x as well. Now, we didn't actually need to draw the line y equals negative x for the reflection because we know the patterns that go along with reflecting in y equals x. But I did want to show you the angle between that and the y-axis. And it's the smaller of the two angles because there's this angle here and there's this angle there. We want to use this angle, and that would be a 45-degree angle, right? Okay, so what our conjecture here then is going to be is that the final image after we reflect in this line followed by this line, it's going to be a rotation, and it's going to be twice this. It's going to be a 90-degree rotation from the original figure about the origin, because that's where our two lines intersect one another. Well, let's go ahead and use our pattern for reflecting a figure in the y-axis. Remember, when you reflect on the y-axis, you keep the same y-coordinate, but you just make the x-coordinates opposites of one another. So here would be B prime, here would be A prime, and C prime. And just to make the next reflection easier, I'm going to go and write the coordinates down for those points. So that's our reflection in this line. Now let's do the reflection in this line. And we switch the order of the coordinates and change the signs whenever we reflect on the line of y equals the opposite of x. So negative 1, positive 6 would get mapped to negative 6, positive 1. There's your B double prime. The point 3, 6 would get mapped to negative 6, negative 3. There you go. I just realized I didn't go up 1 unit for B double prime. Let's move that up there. That was where the negative 6, negative 1 was. Or negative 6, positive 1, excuse me. And then we're going to reflect the point 3, 4 to negative 4, negative 3. And that gives us the final coordinates of our image at these coordinates right here, which, by the way, I mislabeled down here. I put the points in the right place as far as where they're physically located, but this is where C double prime is supposed to be. I'm going to switch that with, switch those two around. Much better. That will go this way. Now your eye might not be trained enough, but part of the reason I made this triangle a right triangle is so you could see that indeed we had a 90-degree rotation. You could actually turn your screen if you're on a mobile device, and you would see that the triangle right here, if you rotated 90 degrees, would look just like this after you were done doing so, right? Okay, so we did the double reflection in lines that were 45 degrees apart, and it resulted in a 90-degree rotation about the center, or about the intersection of those two lines. Now I'm going to prove that by saying, hey, what if we take the original coordinates for triangle ABC, and we apply the pattern for a 90-degree rotation to them? Well, let's do that. All right, so remember, whenever you do a 90-degree rotation, counterclockwise, because again, that's what our textbook always uses, you always just put the opposite of the y-coordinate first and then the x-coordinate second. So that means that A, after a 90-degree rotation, would go to negative 6, negative 3. All right, so you see that matches up with our A. Well, hold up. All right, and then B would go to negative 6, 1. And then C would go to negative 4, negative 3, which does match up with what we have on the figure. I mislabeled them a little bit right there. But nevertheless, you can see that whenever you reflect twice in intersecting lines, that you end up with the last figure being a rotation of the first figure, and the angle of that rotation was twice the angle formed by those intersecting lines. All right, that's double reflections. Thanks for your attention. See ya.